This is Juno 5 AS1, question 3, another projectile question. Figure 3.1v is a vector of magnitude v, making an angle theta with the x-axis. On figure 3.1, draw construction lines showing how to obtain the x and y components of the vector. Label the magnitudes of the components clearly. So if we just put this in here, you know you have to split that into two components. And you split them in. I taught you to do this as a vector triangle, like that. And they have to be at right angles to each other, which is absolutely fine. You could also, in maths, I know what you do is you do a horizontal one and a vertical one where the velocity starts like this one here. So I'm just putting it in as an alternative. That would be an alternative. So this is beside the angle, and so this is a V, and it's the one with the cos in it. And this one is opposite the angle, so it's going to be V sine theta. And obviously if you labelled this one here instead, then it would be V sine theta also. So you have to label the magnitudes clearly. If you don't label them, you lose a mark. And that's really annoying. In part B and C of the question, ignore the effect of air resistance. An object is projected from the point P with a velocity v at an angle of theta to the horizontal. It follows the path as shown. The point Q is at the top of the path. Complete table 3.1 to show the values of the vertical and horizontal components of the velocity at points P and Q and the value of the vertical acceleration of the object at these points. Take the upwards direction as positive for both velocity and acceleration. Now, if you think what's happening there, you can see there that the vertical velocity is going to decrease going up and then increase going down. Now, the value of the acceleration, which is something we're going to have to put in, acceleration always points downwards. And so if the upward value is positive, then the acceleration in this case is in minus at all places there. And therefore, we are going to be putting well, at all places up to Q anyway, we're going to be putting our acceleration in as a negative value. So the vertical component of the velocity then, and we've got it from this diagram here, is going to be V sine theta. The horizontal component of the velocity is our V cos theta. And our acceleration here is going to be minus 9.81. Now, at point Q, we look there, point Q, it's at its maximum height, its vertical velocity has decreased to 0, its horizontal velocity hasn't changed, and it's still subject to an acceleration of minus 9.81. And so that is going to be 0, horizontal hasn't changed, and acceleration is still minus 9.81. Part C. A long jumper runs up to the takeoff board. He takes off the launch angle of 30 degrees and achieves a jump of 7.8 metres. Treating the jumper as a point object shows that his takeoff speed is 9.4 metres per second at an angle of 30 degrees. And it gives you a hint. Combine the equation with the time taken to reach the maximum height with the equation for the time taken to for the horizontal distance travelled in this time. So in that time, maximum height, it says the time taken to reach the maximum height. So we'll write a few things down. So that's a vertical, all the vertical components. So vertically, his initial velocity is V sine theta, which is 30 degrees. We're trying to prove a value for V, that the value of V is 9.4. You know that his final velocity at his maximum height is 0. You know that A is equal to minus 9.81. And we're looking for T. And so if we were looking for T, we would rearrange our V equals U plus AT equation to give you V minus U over A. And so that is 0 minus V sine of 30 over minus 9.81. Horizontally, we're actually getting the range to halfway position because that's where his maximum height is. And so the distance travelled is half of 7.8, which is 3.9 metres. The takeoff speed and the speed throughout, I'll just call it U, is equal to V, which we're trying to find out, and it's the cos of 30 degrees. And we don't know the time, but we do know that the times for the horizontal and vertical parts of that motion have to be exactly the same. And therefore, if we know that time is distance over speed, I'm going to write u there as speed, and that is 3.9 over v cos 30. Then we can put these two times equal to each other. And so if you put those two times equal to each other, you're saying minus v, the sine of 30, over minus 9.81, and the minuses cancel, is equal to 3.9 times v cos 30. Okay, so that comes out to be 0.05v is equal to 4.5 divided by v, and therefore v squared is equal to 4.5 over 0.05v, and v then comes out to be 9.4. So there's quite a lot of working out in that question there to get that answer. So all you've done there is put the times equal to each other, but first of all you had to come up with an equation for time for each one, and that was the difficult part. Part 2 of the question, the jumper reviews ways of improving his performance. He thinks that the length of his jump may be increased either by changing his takeoff speed and jumping at the same angle, or by changing his launch angle and jumping with the same takeoff speed of 9.4. Calculate the percentage increase in the length of jump that would be achieved by increasing the takeoff speed by 5% and jumping at the same angle 30. So our new speed then, new initial vertical velocity, or the new velocity should I say, is equal to 1.05 times 9.4. 1.05 coming from 105%, so it's 105%. That's equal to 9.87. Now, the easiest thing for you to do is just to do, first of all, calculate your new range using that complicated equation, the sine of 2 theta over g, v squared the sine of 2 theta over g. And that's equal to 9.87 squared by the sine of 2 theta. Theta is 30 degrees, so it's the sine of 60 degrees over 9.81. And that gives you an answer of 8.6 metres. And therefore the percentage increase is the difference between the new and the old, which is 7.8, divided by the old and multiplied by 100%. And that gives you an answer there of 10.3%. And that's your answer. I'll just scan in a wee bit so you can see it a bit better. Part 2, the maximum range of projectile is obtained when the angle of projection is 45 degrees. Calculate the percentage increase in the length of the jump that would be achieved by increasing the launch angle from 30 to 45 degrees and jumping at the same takeoff speed. So we're going to do our r is equal to v squared, the sine of 2 theta again, over g. And that we're keeping the same takeoff speed, 9.4 squared. And that will become the sine of 90, which is 1 over 9.81. And that range comes out to be 9 metres exactly. So the percentage increase is the 9 metres minus the original 7.8 over 7.8. And you're multiplying by 100%. And that comes out to be 15.4. So obviously that's greater. So you're going to get a better result if you increase your takeoff angle. But you should find that your answer to 2 is greater than that of 1, which was 10.3. However, the athlete decides to train so as to increase his takeoff speed rather than his launch angle. Suggest a reason. And the reason is, of course, that it's very difficult to launch at an angle of 45 degrees because you have to work against gravity. Work has to be done against gravity. And so it's easier for the athlete just to increase his speed.